All right, so I think this is recording. Let's take a look here at number 2. We have two rational expressions. We're multiplying them together. They want us to simplify that, but to also state any restrictions that we have. Restrictions come from the fact that since we have variables in the denominator, we want to make sure that we never have division by 0, that we can't have a 0 in our denominator. So I'm going to start out by taking these two fractions and writing it as a single fraction by doing the multiplication. So in my numerator, I'm just going to multiply these two numerators together. I'm going to put parentheses around them. And I'm just going to write it like that. I'm just going to write it x squared minus 10x plus 25 times x minus 10. And in the denominator, I'm going to do the same thing. I've got this binomial, which is 10x minus 100 times 45 minus 9x. Well, it's kind of difficult to see my restrictions because the numbers are kind of big. It's difficult to see what would cancel because I really don't have things in factored form. So let's come off to the side and start looking at these expressions and see if we can't factor them. So let's start with this trinomial. X squared minus 10x plus 25. Now, that looks familiar because remember when we were doing completing the square, if I take half of negative 10, I get negative 5. And if I square it, I get 25. So even though the x method will help me out here, I can easily see that this guy is a perfect square trinomial, that it factors to x minus 5 times x minus 5, or x minus 5 squared. All right, so let's look now at the denominators. This binomial, 10x minus 100. Well, let's write 100 as 10 times 10, and we can see that a 10 is common to both terms. We can factor out that common 10. What we have left in the first term is just an x, and in the second term, a 10. And let's take a look at this binomial 45 minus 9x. But let's rewrite 45 as 9 times 5. And we've got 9x. And what do you know? We have a 9 that's common to both terms, and we can factor that out. What we have left in the first term is just a 5, and in the second term, minus x. So if we rewrite these expressions in factored form, we'll be able to see things a lot more clear. So we've got x minus 5. And I'm even going to write it, since it's squared, I'm just going to write it as x minus 5 times x minus 5. And then I've got times x minus 10. And in the denominator here, this 10x minus 100, we said that it factored to 10 times x minus 10. And this 45 minus 9x, that it factored 9 times 5 minus x. All right. So here in factored form, I can see a lot of different things. Maybe sometimes even too much at once, but let's focus our attention on the denominator and state our restrictions. We do not want this denominator to ever equal 0. So if x were allowed to be 10, 10 minus 10 is 0, and 0 times anything would be 0. So I have to definitely prevent x from being 10. And over here, 5 minus x, what if x were 5? 5 minus 5 gives me a 0. So I know that those are my two restrictions. Now let's come in and cancel common factors. I see an x minus 10 and an x minus 10. And at first, that's all I see. So let's write that. In the numerator, I have x minus 5 times an x minus 5. And in the denominator, I have 10 times 9 times 5 minus x. But let's look at that 5 minus x. Oh, and don't forget, we have our restrictions. I want to think about 5 minus x. Let's come off to the side and 5 minus x. The addition is what we call commutative. It doesn't matter the order that I add things together, but subtraction, the order is important. And I know that 5 minus x is not the same thing as x minus 5. But I do know how to make them equal. I know that 5 minus x is the opposite of x minus 5. When you change the order of the subtraction, you make an opposite. Let's plug in a number and I'll show you what I mean. If I had, say, 3 minus 1, 3 minus 1 is not equal to 1 minus 3. 3 minus 1 is a positive 2, and 1 minus 3 is a negative 2, and positive 2 is not equal to negative 2. But what if I said that 3 minus 1 is equal to the opposite of 1 minus 3? Isn't this true, that 2 is equal to the opposite of negative 2 is a positive 2? So when I have subtraction, I'm not, and the subtraction is in a different order, I'm not going to say that they're equal to each other, but I am going to say that they're opposites of each other. And by using that idea of the opposite, I can set up an equality. So this 5 minus x, I can think of it as a negative 1 times x minus 5. Well, why would I do that? Well, let's come back over here. I've got x minus 5 times x minus 5. I have 10 times 9 times, and this 5 minus x, I'm going to rewrite it as negative 1 times x minus 5. Now, of course, I have my restrictions. Now, I'm going to shrink this up because I have run out of room. Just when we got to the exciting part. All right. So remember before, I didn't think that I was going to be able to cancel 5 minus x with x minus 5, but it turns out, since they're opposites, they divide to negative 1. So I can cancel x minus 5 over x minus 5, and I can say that I have x minus 5 divided by, well, these are just numbers, so I can multiply them together. 10 times 9 times negative 1 is a negative 90. And there's nothing wrong with that answer. I can leave that answer like that. Now, a lot of times, people will take that negative sign and move it up to the numerator. But I'm just going to leave it right where it is right there. That's fine. No one can say that we're wrong. There we go. All right, that's our final answer. Don't be afraid to ask questions. I hope this helps, and I'll talk to you later. Bye.